All right, guys. So, yeah, let's see here. So this is Math 4B, Lecture 1, which is going to be on exponentials. I'm your instructor, Greg Hogan. So the way that lectures are normally going to be, hopefully in a couple of days from now, are going to be fully electronic and not like this using a document camera. But for right now, today, this is what we have. Also, because I've been running behind, I have some typed up notes here, but I'm not going to be using these today just because this set of notes that I've typed up last semester has derivatives of inverses, which we're not ready to do yet, and then goes into properties of exponents and logarithms and that kind of thing. And I don't have the couple hours it would take to separate this out into different notes, different sets of notes for each lecture. So I'm just going to handwrite these right now, and I'm still going to post the full notes for you in the next day or two so you can have them. Um, yeah, but for now, I'm just going to handwrite these. So I'm just going to use these as a reference for myself. Um, yeah, anyway, we'll try to get started here and see how it goes. So, um, what you've got for your first day of lecture is exponentials, and specifically what we need to cover are just kind of basic exponential stuff, and some stuff regarding derivatives. Okay, and so this is one homework set in Newton Alta, very quick, and this is another set in Newton Alta, and it's a little bit slower. But that's what we're going to be working on today. So we'll start with basic exponentials. So the first thing you're going to be dealing with for an exponential function is this. So exponential. All right. There's going to be a couple of different ways you can write an exponential. So you can have an exponential written this way. Uh, there's more than one form. You could have like f of x equals a b to the x. This is an exponential function. Or you could write them as kind of like, let's say, k, I don't know why I use k, c e to the kx, something like that. The exact names for the constants doesn't matter. So you could write them this way or this way. They're equivalent, so it doesn't really matter. So you could say y equals 3 times 4 to the x. That's an exponential function, but also y equals 3e to the 2x. That's an exponential function. You're used to seeing them this way, but they could be this way as well, and either way, they're exponentials. All right? Now, what you're going to have to do on the homework is pretty easy. They're going to ask you to match up the graph of an exponential function with the function that it came from. So they give you the function, and then they make you pick the graph out of 4 choices. So let's see if we can graph an exponential real quick. So let's say we want to graph an exponential that looks like this. Example. Graph f of x equals, let's say, 2 times 3 to the x. Okay? Now, if they want you to graph that, all you need to do is get a couple of points on the graph and then graph it. And it's really easy. So if you make a table of values, you honestly don't need to pick a lot of values. Just pick maybe like -1, 0, and 1 for your x values. That's already going to give you a good enough graph. I'll go up to 2 just so you can see, but this is going to give you a pretty good graph already. So if you take these numbers and you substitute them in here, so you put the -1 in here, you have 2 times 3 to the -1. You have to remember what a -1 exponent means. That means it's in the denominator. So this is actually 2 times 3 to the -1 is actually 2 over 3 to the 1. So that's 2/3. When you put in a 0 here, you have 2 times 3 to the 0. 3 to the 0 is 1. So this is 2 times 1. So that's 2. Put in a 1 for x, you have 2 times 3 to the 1. Of course, that's just 2 times 3, which is 6. Put in a 2, you have 2 times 3 to the 2, which is 2 times 8, no, 2 times 9. I was going to say 18, not 8. But 2 times 9 is 18. There you go. So you just get a couple of values like this, and then you should be able to make your graph. So let's see here. I didn't go very far out on the x-axis. I'm going to go 1, 2, and that's it. 1, 2, and that's it. The y values get pretty big, right? They go up to 18 here. So I'm going to go 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Okay, so there's my graph. And then we just plot the points. So I've got 2, 18 here. So that's 2, 18. That's about there. A little too far over to the right, but that's fine. 1, 6. 2, 4, 6. About there. Uh, 0, 2. That is right there. -1, 2/3. 2/3 is very small. That's about, these are negative. It's about there. And then as you go out this way, we didn't plot it for -2, but if we did, it would have been 2 over 9 or something, very close to 0. And so what you get is out in one direction, this graph is almost a horizontal line, very close to 0. And then on one side, it becomes very steep and grows quickly. And this is a typical exponential graph. And so it's not hard to match these up. Typically on the graphs that they show you, you're going to be able to see a couple of points. So you'll just plug in a 0 and make sure this point is in the right place, and then maybe plug in a 1 and make sure that this point is in the right place. And if the 2 points are in the right place, then you'll have the correct graph. So it's not that bad. Now what they can do is they can make your life a little bit harder by making you graph something like this. So let's say plot y equals, I'm going to say 2, 3 to the -x. I don't know why I put a 2 there. I'm going to change that. I'm going to put a 1/2 there, just so it's different. All right? And again, if we want to plot this, we don't need a lot of points, we only need a couple. So let's pick a couple of x values. Again, I'm just going to pick 3 and then work it out. So I'm going to take these 3, plug them in here. You have 1/2 3 to the -1. So you've got that negative there, and then you've got that negative there, and so there's 2 negatives. So this is 1/2 3 to the 1, which is just 1/2 to the 3. Wait, I said 1/2 to the 3, that's not right at all. That's 3 to the 1, which is 3, and then 1/2 times 3. 3/2. Right. Put in a 0. Put in a 0 here, you have 1/2 3 to the negative 0. So that's 1/2 times 1, which is a half. Put in a 1 here, you have 1/2 3 to the minus 1. Remember what a negative exponent does. It means it's upside down, so this is 1/2 times 1/3. 3 to the negative 1 is 1/3. 1/2 times 1/3 is 1/6. So if you want a very basic graph, there we go. Only counted up to 3 this time for the y values, and let's put the points in. Negative 1 comma 3/2. Negative 1 comma 3/2. That's 1.5. It's right there. 0 comma 1/2. That's there. 1 comma 1/6. That's here. And if you plotted a few more points in the negative direction and a few more points in the positive direction, what you would see is that this levels out to the right. And then this side goes up. So it's the same basic thing as the other graph, but this one's kind of the mirror image left and right. And the reason that is the case is because of the negative x there. The negative x literally just flips the graph around and flips the graph around, makes it the mirror image of itself. So anyway, that's what you have to do in the homework. It's pretty straightforward. The only other thing you have to do in that first homework assignment is use the properties of exponents. So properties of exponents are as follows. So if you have a to the m, a to the n, how does that work out? Hopefully you know this. You add the exponents. If you have a to the m to the n, then you multiply the exponents, a to the n. If you have ab to the m, if you have two things to the same exponent, then you can distribute that power onto both of these and have a to the m, b to the n. If you have a to the m over a to the n, this is a lot like the first one, but this one you subtract the exponents. If you have a over b to the m, then just like the a times b to the m, you can distribute that m power and have a to the m over b to the m. What else do we have? If you have a to the minus m, that's the same thing as 1 over a to the m. And so we actually used this one here when we did 3 to the negative 1 and we wrote it 1/3. All right, so those are pretty much your properties of exponents. There are a couple others involving like roots and stuff, but we're not talking about roots at the moment, so I'm not going to write them right here. So there are your properties of exponents. The question is, what are we doing with them? And basically all you have to do in this section is just simplify things like this. Like if they say, example, simplify And they might do something like um, x to the 3, y to the negative 2 over z to the 4 times, let's say, z to the 1 over y to the 3x. Right? So simplify this. This is just an example. If you have to simplify something like this, then you want to apply your rules and properties of exponents to just move stuff around and combine the different z powers, combine the different y powers, combine the different x powers, basically. That's all you need to do. So what you would do is just rewrite this as one fraction. I guess I'll do this like this. So you have x to the 3 on top, y to the negative 2 on top, z to the 1 on top, 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 bottom, bottom, bottom. Z to the 4th, y to the 3rd, x to the 1. So you've got all your stuff written in one fraction. Well, multiplication is commutative, which means I can change the order that we write these in on the top and the bottom here. So I can just put my x's together, like x over 3 is on top, and then there's another x on the bottom. And then for y's, there's a y to the minus 2 on top, and a y to the 3 on the bottom. And z's, there's a z to the 1 on top, and a z to the 4 on the bottom. From there, we can apply our powers, our rules. So basically the only rule that we need for this problem is this one right here. When you have a to the m, a to the n, you subtract those exponents. First, top one first, bottom one second. So if you apply that rule here to each of these three, then you have x to the 3 minus 1. If you apply that rule here, you've got y to the minus 2 minus 3. It's a little bit confusing, but this was a minus 2, so it starts out with a minus 2. And then z, 1 minus 4. So you do the subtraction on the exponents, you get x to the 2, y to the minus 2 minus 3 is minus 5, z to the 1 minus 4 is minus 3, like that. So we've simplified all the exponents. And then the other thing we can do is we can apply this property right here to anything with a negative exponent can be written in the denominator. So these two have negative exponents, so you can move them to the denominator as follows. So put the x to the 2 in the numerator because it had a positive exponent. Y to the minus 5 is y to the 5 in the denominator. And z to the minus 3 is z to the 3 in the denominator. And that is simplified. All right? Now, I mean, I could do more of these with different powers, or sorry, not powers. I could do these involving different properties. I don't really want to do that because I want to get into the derivative stuff. So I think we'll do that. So let's let us look the derivative of exponentials. Lost a piece of paper here, so I'm just looking for it. All right. So let's look at derivative of e to the x. That's what we want to start with. Okay, now here's the thing. If I want to do the derivative of e to the x, and I don't know what the derivative of e to the x is at all, then we can do this. Derivation. Haven't done this in a while, let's hope for the best. So I'm going to say my function here is e to the x, and I want to find f prime of x, the derivative of e to the x. Now, we don't normally use the definition of the derivative, and we're not going to use it very often in this class, but we're going to use it right now just to give you the idea of where this comes from. So, if I want to find f prime of x with the formal definition of the derivative, it goes like this. So here's the definition of the derivative. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. Now you probably remember this vaguely, but it was probably a while back for you. It's towards the beginning of your first semester calculus class. But let's try to use this formula with this f. So if f of x is e to the x, this is the limit as h goes to 0 of f of x plus h is e to the x plus h minus f of x, that's e to the x, over h. All right, now then you've got these two exponentials, and you're trying to do something with them. That's where you need those properties of exponentials again, right? We've got a formula here. Look at this first property, a to the m, a to the n, a to the m plus n. Well, normally we can take these and combine them into one exponent like this, but you can use this formula backwards to, if you have an a to the m plus n, you can split it up into two a's, a to the m, a to the n. And that's what we want to do here, because we have e to the x plus h. That should be e to the x, e to the h. So you just apply a property of exponentials. I'm not going to write that, but that's what it is. And you can rewrite this as e to the x, e to the h, minus e to the x over h. Then you should realize that these both have an e to the x now. That means you can factor out an e to the x. So you get that. But then what you can do is you can realize that the limit is h goes to 0, right? H goes to 0, not x goes to 0, right? So this limit actually has nothing to do with e to the x. It has to do with h, which is over here in this part. So since this doesn't have an h in it, this can actually come out in front of the limit. So you get this. E to the x times limit h goes to 0, e to the h minus 1 over h. Now, this right here, we actually do not have a way to calculate this at the moment. But this is just a number, okay? What number? Now, like I said, we don't know what it is, so we'll have to figure out how to do it. We're taking the limit as h goes to 0 though, right? So if you wanted to approximate it, you could plug in a number that was close to 0 in here for h, and you can just see what it is. So just off to the side here, I'm just going to plug in h equals, let's say 0.001 into this. I would have e to the 0.001 minus 1 over 0.001. And I'm going to work this out on a calculator, if I can find my calculator. Here it is. So if I try to work this out, e to the 0.001, oh, come on, don't tell me anything. Okay, there we go. 0.001, enter. Where is button? Okay, there we go. E to the x. So this is like 1.0010005 something minus 1 over 0.001. So you work this out, subtract, and then divide by 0.001, and then this works out to 1.0005017. Now, this is not the limit, right? This is the limit as h goes to 0, and I just put a small number in for h. So this is not the limit. But hopefully you can see that what we got was a number that was really close to 1, right? And if you make this even smaller, like 0.00001 or something, then the answer here becomes even closer to 1. And so what you guess here is that this limit is 1. And that's what it is. So this limit works out to 1, and you get e to the x. So what did we just discover here? We discovered this. If f of x equals e to the x, then f prime of x is what we just did, e to the x. That's a very, very simple formula. The derivative of e to the x is e to the x. Okay? So now you know it. So you put that on the list with the other derivatives that you know. Okay, so you got to remember all your derivatives from Math 4A. So we know this. Derivatives. We know. Here are some of them. The derivative of a constant, 0. Of course, the derivative of x is 1. I don't need to write that. I should have just written the power rule, which is here. The derivative of x to the n is nx to the n minus 1. There's your power rule. And you know the derivatives of all the trig functions. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. The derivative of tangent x is secant squared x. 3 more. The derivative of, well, what haven't we done? Secant. The derivative of secant x is secant x tangent x. The derivative of cosecant. Scribble, scribble, scribble. The derivative of cosecant x is negative cosecant x cotangent x. Yikes. And one more, the derivative of cotangent x is negative cosecant squared x. Okay, so we know those derivatives, we know the power rule, we know that's about it. We do also know the chain rule and the product rule and the quotient rule, which I'll also write here. So we should also know the derivative of f of x, g of x is f prime g plus f g prime. That's the product rule. One way to write it. We need to know the quotient rule. I'm sure we'll be writing these down more. The derivative of a quotient is f prime g minus f g prime over g squared. And chain rule, which is the derivative of f of g of x, is f prime g prime x. Okay, so to all of these rules, we add this one, right? All we're doing is we're taking all of these derivatives that we know and we're adding onto the list d dx e to the x is e to the x. Okay, and initially that's going to be very easy. I think the homework kind of jumps in and makes you do product rule and quotient rule and stuff. But we'll do a couple simpler examples. So if I ask you to find, if I say f of x equals, let's say, 3x to the fourth minus 2e to the x. I say find f prime of x. Then that should be easy, right? What you're supposed to do is you're supposed to say, okay, well, I do the derivatives term by term. So first I do the derivative of 3x to the fourth. Well, I'll even do this even longer here. Right? You do that derivative first, and you do this derivative second. So, how do you do this derivative? Well, it's 3x to the fourth. You just need the power rule. So you bring the 4 down in front, combine it with the 3 that's already there and get 12. Subtract 1 from the power, get 12x to the 3 minus, now you need the derivative of 2e to the x. Well, the derivative of e to the x is just e to the x. So the derivative of 2e to the x is 2e to the x. And that's it. That's as easy as it comes. Okay? Now, you should be able to handle exponentials with the chain rule as well. Right? Like what if you have f of x equals 3e to the tan x and you need f prime? Well, how do you do that one? Well, that's where you need the chain rule. So the chain rule says when you're taking the derivative of a function in a function, you take the derivative of the outside function first, leave the inside function the same, and then you tack on the derivative of the inside function. So what does that look like? What that looks like is, well, the 3 is along for the ride, and you would say, well, e to the tan x. Well, what's the derivative of e to the x? The derivative of e to the x is e to the x. So the derivative of 3e to the tan x is 3e to the tan x, right? Because the derivative of e to the x is e to the x. However, the chain rule makes you multiply by the derivative of what's inside. So what's inside was this tan x. So your chain rule part is what's the derivative of tangent x? Answer, secant squared x. So you get 3e to the tan x secant squared x. That's your derivative. Okay? So you need to be able to do the chain rule. with e to the x. Maybe I should have done an easier one, something like this. Like I could just say evaluate. I'll say like d, let's change the variable, t. E to the t to the fourth, right? All you're doing is you say, well, what's the derivative of e to the x? Derivative of e to the x is e to the x. So the derivative of e to the t to the fourth is e to the t to the fourth times, for the chain rule, the derivative of what's inside. So you need, what is the derivative of t to the fourth? 4t cubed. All right? So, that's a little bit tricky for some people. You remember that the derivative of e to the x is e to the x, and then you forget to throw this on the end. All right, let's do quotient rule or product rule. Let's try product rule. So let's say I want to do this derivative, the derivative of x cubed e to the 2x. Well, to product, they're multiplied, so you have to remember the product rule. Now, you can remember it written out in like a complicated form like this. However you remember it, you need to remember it. So how do you do it? Well, like this is your f and this is your g basically. So the way I do it is I say f prime g plus f g prime. So what I'm doing is I'm putting a prime on the two pieces that still need me to take a derivative of. And that's how I tend to write the product rule when I'm writing it for myself. There's your product rule. And then we've got to take this derivative and this derivative, both easy. So what's the derivative of x cubed? 3x squared. What about this? Well, there's no prime on it, so you're just rewriting it. Plus, what's the derivative of this? Who cares? There's no prime on it, right? We're not taking the derivative of this. So just rewrite it. Okay, now we need the derivative of e to the 2x. Well, what is the derivative of e to the 2x? Well, the derivative of e to the x is e to the x. So the derivative of e to the 2x is e to the 2x, but then the chain rule makes you multiply by the derivative of what's inside. So you multiply by the derivative of the 2x, which is 2. So 3x squared e to the 2x plus 2x cubed e to the 2x. That's your derivative. Okay? Now, what else? I think the only thing else that I want to make sure that we do is we want to talk about, well, where is it? Well, I don't know if it's in the in your homework set or not, so maybe you have to do this and maybe you don't. But the derivative of a to the x. So remember when we just derived the formula here for the derivative of e to the x? We did this limit for the definition of the derivative. We got e to the x times a limit, and this limit turned out to be 1. Well, it turns out that if you change the e to some other number, remember e is just a number, it's 2.7 something. If you change that e, then that doesn't work out to 1 anymore. It has a slightly different formula. So, the derivative of e to the x is e to the x. But the derivative of a to the x is a to the x ln a. So this is what happens to that limit. Instead of being a 1, it turns into ln of a. And I'm not going to derive that or anything, but you can work it out, and that's just what it works out to. So both of these can be used in your calculus problems, right? So here's an example. Evaluate. I'm just going to say find, sorry. Example. Find f prime if f of x equals, we're going to say 3 to the x over 2 to the x plus x. Okay, so this is going to be a pretty complicated one. We're going to take this derivative, f prime of x equals, and we need the quotient rule. So the form for the quotient rule, I wrote it one way. I guess I'll write it that way again. So here's how I wrote the quotient rule. F prime g minus fg prime over g squared. We just start with f to f prime. Other people remember it differently. They remember that you start it with the bottom times the derivative of the top. That's fine too. Just have to remember it somehow. So that's the rule we're applying here. So I need f prime g. So for the purposes of the quotient rule, this is f and this is g, even though I called the whole thing f. So f prime. So f prime g. F prime g minus f g prime all over g squared. So that's what my quotient rule says to do. And then to finish this off, all I have to do are take two derivatives here, the two things that have a prime on it. So the derivative of 3 to the x. Well, very simple formula. The derivative of a to the x is a to the x ln a. So the derivative of 3 to the x is 3 to the x ln 3. So the derivative of 3 to the x is 3 to the x ln 3. Then you've got the 2 to the x plus x minus 3 to the x. Then you need the derivative here of 2 to the x plus x. Put that in parentheses. So what's the derivative of 2 to the x? Well, again, simple formula. 2 to the x ln 2. Then you need the derivative of x, which is 1. All over 2, I wrote 2x. 2 to the x plus x squared. All right, so there is your derivative. Now there's not a lot you can do here to simplify this, I don't think. What you can do is everything up here has a 3 to the x, so maybe you want to factor out a 3 to the x. Then maybe you could distribute this ln 3 through here. ln 3 times 2 to the x. ln 3 times x. Then you've got minus, well, we factored out the 3 to the x, so minus 2 to the x ln 2, and then minus 1. And that's probably as much as you can simplify that. There's not a lot you can do. All right? And so that's pretty much your first assignment. It's just derivatives involving exponentials and then a few graphing exponentials problems. The um, hard part is going to be remembering all of your derivative rules, which I need to post something for you guys, like a list of common derivatives and integrals, um, and so on. Something I'll recommend if you have trouble on the homework is you ought to um, check out these two websites. So www.symbolab.com and www.wolframalpha.com. Now, both of these sites will let you, have the computer calculate derivatives and stuff symbolically for you. Symbolab will show you work, like for the product rule and that kind of stuff, whereas Wolfram Alpha just gives you the final answer. You shouldn't use these to do every problem on your homework, of course, but your homework is adaptive, which means that if you do one problem right and then one problem wrong and then one right and then one wrong and then one right and then one wrong, you're going to be doing it forever, because as long as you keep getting them wrong, the online homework system says, oh, well, you don't quite get it. And you might understand perfectly, but you just keep typing in the problem slightly wrong, or you drop a 2 on accident or something, right? You can understand it and still get the wrong answer. And so if that starts happening to you, then you might want to check your answers in one of these sites before you type them into Newton Alta. That way, you don't have to get the problems wrong and take longer on your homework. Okay? I'll do a demo of that in the next couple of days. I just need to catch up with the video posting, and then we'll do that. Anyway, I think that's it for today. So I'm going to turn this off and get this posted for you guys.